which is coated on the inert
This call is now
gas
being
and
recorded.
solid gas,
This call is now
and the
taking
mobile
notes.
phase is in inert gas. The instrument requires several components: an injector, a column, a detector, and a recorder. Now, let us take a quick look at applications. That the gas liquid chromatography is a powerful tool with a wide-ranging applications, including environmental testing, food flavor analysis, forensic and pharmaceutical analysis. Now, moving on to the next slide, we have the comparison for all the four types of chromatography. As you can see here on the screen, for paper chromatography, stationary phase is paper, and for mobile phase is solvent, and the types of separation is partition. And for the TLC technique, we have stationary phase as silica and alumina, and mobile phase as solvent, and types of separation is adsorption. As you all are familiar with adsorption, it is a surface phenomena where the particles get attached to the surface. Okay, and the column techniques, we have the same silica and alumina, and mobile phase is solvent, and also the type of separation is adsorption. And for the gas liquid chromatography, as I've already mentioned, the stationary phase is liquid film on solid support, and the mobile phase is gas, and the types of separation is volatility. Now, I would like to conclude my presentation by saying that chromatography is an essential technique for separating, identifying, and purifying the components of a mixture. Each type we have discussed, that is paper, TLC, column, or GCL, serves a unique role from simple analysis to advanced purification, and it remains the vital tool in the modern research, pharmaceuticals, and environmental analysis. Now, before ending my presentations, uh, this is the references from where I have brought all the information from, as you can see here on the screen. And before ending the presentation, I would like to express my sincere gratitude to the organizing committee for providing such a wonderful opportunity to perform my presentation or a work. And my heartfelt thanks to my teacher, my guidance, Dr. Homnath Luitel sir, also the HOD of the department, for his constant guidance, encouragement, and the valuable support, and also my friend. So thank you all for paying kind attention and support. This is the end of my presentation. Thank you.
Thank you, Sita. Congratulating you. But your chromatography, can the colloidal substance can separated by chromatography?
Yes, sir.
Colloidal substance, can
Yes,
you
sir.
separate out by this chromatography?
So colloidal solution. Yes, sir, it can be separated by the forms of chromatography, which is particularly it based on the size, sir. SEC, which is a size exclusion chromatography, which I have not included in the presentations.
Okay. Okay. Any other question from the audience, please? No questions. Thank you, Sita. Thank you. Once again.
Thank you, sir.
Next, I invite Tasi Chen Lepcha. Yes, go ahead.
Hello,
Yes, yes.
am I audible?
Yes, yes.
Okay, good evening, everyone. My name is Tashi Sitin Lepcha, and today I will be presenting on fast protein liquid chromatography, or simply known as FPLC. It is very interesting and powerful method used to separate and purify protein, something we use a lot in biochemistry research. This presentation was prepared under the kind guidance of Dr. Homnath Lutel. I'll be presenting, explaining what FPLC is, how it works, its main part and advantages, and where it is used. So first, let us answer the basic question, what is FPLC? It is a type of liquid chromatography that is very gentle and protein friendly. It was first developed in 1982 by a company called Pharmacia. FPLC help us to separate and purify proteins and other biomolecules without damaging them. So you can say it is a bridge between old style column chromatography and high speed liquid chromatography. Not too slow, not too harsh. That's why FPLC is now found in almost every research lab. It saves times, gives accurate result, and keeps protein safe. So now, how does FPLC really works? The secret lies in separating molecules based on their properties. So there are four main ways of separation. One is size exclusion, which separates by the big molecules and by comparing the big molecules and small one. So big molecules move faster and the small takes longer time. So next one is ion exchange, which the separation happen by charge differences. Affinity chromatography, specifically it separate by seeing the specific biological binding like enzyme and substrate. And the another one, hydrophobic interaction, which is based on how much molecule like or dislike the water. So the main component of FPLC system, okay, and an FPLC system is made of several parts, as you can see in the picture. An FPLC system is made of several parts all working together like a small orchestra. The pump control the flow of the buffer. As you can see, the injection valves put in the sample with the accuracy. And inside the column, the protein gets separated and the UV detector keeps checking which protein is coming out, and the fraction collector neatly collects them in the small tubes. Finally, this buffer mixer makes sure everything flows smoothly. Hello? Hello?
Yes, yes.
Is the slide is changing?
No.
No, okay, okay. So sorry. Now?
Yes, it is.
Now? Is it visible?
Yes, it. Yes, yes.
So this is the main component, the component of FPLC system, okay? An FPLC system is made of several parts, as you can see in the picture, all working together like a small orchestra. Here the pump control the flow of the buffer. The injection valve put in the sample with accuracy. Inside the column, the protein gets separated and the UV detector keeps checking the protein, whether it is coming out or not. And this fraction collector collects the protein in the small tubes. So finally, this buffer mixture makes everything flows smoothly without sudden changes. All these part together make FPLC automatic, accurate, and very convenient. So one of the reason scientists love using it. Okay, the slide change. Hello.
No. Not yet. No, not yet.
Oh, what is happening? Okay. So
Yes, it is. Yes, yes.
so
FPL.
so this is the types of FPLC column. Okay. Now let us talk about the heart of the system, the columns. Each column has the special purposes. Sites column, sites exclusion column separate based on the molecular size. Ion exchange column work by charge. Affinity column are like magnet for specific proteins, and hydrophobic interaction column separate based on the polarity. So these columns are usually made up of strong glass and protein that can handle medium pressure. Choosing the right column is like choosing the right tool, it decides how pure and accurate your final protein will be. So let us go to the next slide. So now comes the classic comparison between FPLC and HPLC. Both are like chromatography technique, but they are used for different kind of work. FPLC works at the lower pressure, around 4 megapascal. Using soft agarose bits, it's gentle and safe for large delicate proteins. Okay. HPLC, on the other hand, uses very high pressure, around like 150 megapascal, and a small silica particle. It, it is fast and great for small organic molecules. So we can say FPLC is like a careful scientist, patient and precise, while HPLC is like a high-speed analyst, quick and powerful. But both are equally valuable depending on what we are studying. Okay. So advantages of FPLC. FPLC has many great advantages. It gives high resolution, meaning proteins come out clean and separated. It can handle high salt buffer. It's gentle, so protein stay active. It is fully automated, which saves time and reduces error. And the best part, it has the long-lasting column and flexible flow rate, so it works well for both small and large samples. So overall, FPLC is fast, accurate, and dependable, a perfect partner for the protein purification. So, of course, like everything, FPLC has a few limitations. It cannot handle very high pressure and glass column, need careful handling. It's not suitable for small molecules, and it does not work with HPLC column. Also, the buffer must be prepared carefully to avoid contamination. But if used correctly and carefully, these issues are minor. FPLC still give excellent result of protein work, making it done one of the most trusted technique in the research labs. So here are the applications of FPLC. FPLC can be used in many fields, for research to medicines. It helps in enzyme purification, antibody purification, and many more. It also used in venom protein studies, which helps scientists understand the snake and the insect venom. Basically, anytime we need pure active protein, FPLC is the tool we depend on. It plays a big role in biotechnology and drug discovery too, making it a real backbone of modern biochemical research. So to conclude the FPLC, FPLC is a essential and powerful method for protein purification. It combines speed, accuracy, and gentle handling, keeping protein in their natural active form. It's like the perfect balance between old and new technique, smart, reliable, and easy to use. FPLC continues to support scientists in discovering new enzymes, antibodies, and medicine. So here are the references, key references where I took this, where I prepared this presentation. So lastly, I would like to thank the organizer, Bengal Academic Society for Interactive Sciences for providing us this opportunity for presenting this in front of you all. Thank you. This was all.
Thank you, Tasis.
I'm so sorry
Very,
because of the slides.
it is okay. So, any questions from the audience? Oh, this is late. Okay. Then next is Thomas Chetri. Are you here, Thomas?
Yes, sir.
Yes. You can start your presentation. সে বলে দিয়ে কেটে পড়েছে।
Hello.
Yes, yes.
Yes. Hello. Good afternoon, everyone. Respected teachers and my dear friends. Myself, Thomas Chetri, a student from Narbadur Bandari Government College, Tadung. The topic for my today's short presentation is high performance liquid chromatography and its applications. So, without wasting any further time, let's begin. So, the plan of my talk for today's session is an introduction to what is chromatography, introduction to high performance liquid chromatography, HPLC, its working principle, its instrumentation, its applications, and lastly, its conclusion. So let's begin. So what is chromatography? Chromatography is nothing but a technique for separation of mixture. The mixture we want to separate is dissolved in a fluid which is called mobile phase, which carries it through a structure holding another material called the stationary phase. So as on the right hand side of the screen, we can see the stationary phase, mobile phase, and the sample. So chromatography is perhaps the most influential and analytical technique accessible to modern chemists. Now, what is HPLC? HPLC, high performance liquid chromatography, also referred as high pressure liquid chromatography. The term high pressure is due to the term high pressure is because when we inject mobile phase to the column, we apply high pressure to it instead of gravitational force, which is used in column chromatography. So we can say it is an advanced version of column chromatography. HPLC is used for identification and separation of and quantification of each constituent of a mixture. So HPLC usually uses high pressure to push a mobile phase solution through a column, allowing separation with high resolution. Now, let's dive into the principle of HPLC separation. A small volume of sample mixture is injected into the mobile phase stream. The mobile phase carries the sample column. The components of the mixture interact with the stationary phase, and the different components interact to different extents based on their chemical properties like size, charge, and polarity. It is usually based on a simple principle of adsorption. When mixture of components are introduced into FPLC, they travel according to their affinities. If a mixture has lesser affinity towards a stationary phase, it moves fast. And if the mixture has a higher affinity to stationary phase, it moves slow. So the difference in the movement causes the components to separate into individual bands, which are then detected as they exit the column. Key advantage of high-performance liquid chromatography is it is much faster and more efficient separations with superior resolution compared to other traditional chromatography techniques. The term mobile phase and stationary phase we were talking about are the mobile phase is simply a liquid solvent or a mixture of solvents. The stationary phase is very small porous particles packed into the column. So there are two types of HPLC. One is normal phase and the other is reverse phase. In normal phase, the stationary phase is polar and the mobile phase is non-polar. And in reverse phase, it is the opposite. The stationary phase is non-polar and the mobile phase is polar. This is a table representing the two types of chromatography techniques. As I said that stationary phase and normal phase chromatography is polar. The example is silica, and the mobile phase is non-polar. So the example is hexane. The normal phase chromatography is used for separation of polar compounds. And in case of reverse phase chromatography, the stationary phase is non-polar. Example is C18 bonded silica. The mobile phase is polar. And the example of a polar compound is mixture of water and methanol. It is used for separation of non-polar compounds. So now let's see the HPLC's instrumentation. The HPLC instrumentation consists of solvent reservoir, pump, sample injector, HPLC tube, or we can say column, detector, and lastly data acquisition. This is a block diagram representing all the instrument used in HPLC. We can see solvent reservoir where the mobile phase is kept, and we can see the pump which is used for high pressure. We can see sample ejector part. We can see HPLC tube or column, and it goes through detector, and one part goes to waste and the one part goes to processing unit and display. This is the visual representation of how HPLC looks like in reality. So the instrumentation goes like solvent reservoir and delivery system pump. Solvent reservoir usually holds the mobile phase, and the pump pushes it through the system at a constant high pressure. The sample ejector part is used to inject the sample into the mobile phase. The HPLC column is the heart of the system. It is a stainless steel tube packed with stationary phase material, example, silica particles. This is where the separation part occurs. The detector. Detector detects the separated components as they elute from the column and converts into an electric signal. The electric signal is used by the data acquisition system or the computer, which produce a chromatogram. Let's look closer at the column and the sample analyte. The chemistry of the stationary phase is very crucial. The most common type is reverse phase chromatography of HPLC, where the stationary phase is nonpolar. The example of stationary phase we took C18 bonded silica is a very common nonpolar stationary phase. It consists of long hydrocarbon chains bonded to silica particles. We can see the visual structure of the C18 bonded silica on the right hand side. The example of sample analyte is caffeine. A molecule like caffeine, which is moderately polar, will be separated from the components in the mixture. In reverse phase system, less polar molecules will be retained longer on the C18 column. This is also related to the affinity, which I explained earlier. Now, the data acquisition system gives us a chromatogram. So what is a chromatogram? The output from the HPLC system is a chromatogram, which is a plot of detector's response versus time graph. The x-axis of the graph shows time, which is retention time, which is nothing but the time it takes for the analyte to pass through the column. Each separated component has a unique retention time under constant conditions. The y-axis represents detector response, the signal from the detector. You can see the peaks. Each peak in the chromatogram represents a different separated component from the original mixture. So the applications of HPLC are very versatile. It is widely used across many fields. Likewise, pharmaceutical industries uses HPLC for drug stability, dissolution, study, and quality control, while environmental analysis uses HPLC for biomonitoring of pollutants. Food monitoring and food and beverage industry uses HPLCs for qualitative analysis of soft drinks, and clinical and forensic science uses HPLC for quantitative determination of drugs. The advantages of HPLCs are it is very rapid because of high pressure, it is sensitive, small amount of sample can also be very useful in the HPLC process. High resolution and accuracy is observed and easy visualization. So there are also the limitations of HPLCs. It is very costly. It requires trained operators. The column degrade over time. The silica gel present in the column. Uh, Usually the silica present in the column, which is the stationary phase, get mixed with the mobile phase. So the column starts degrading over time. Uh, The limitations are also it can generate significant solvent waste. So, and it is not suitable for thermally unstable compounds. So at last, the conclusion is HPLC is a powerful analytical technique. It separates component of a mixture using liquid mobile phase and packed column, which is stationary phase under high pressure. It provides fast, efficient, and highly resolved separations. The output chromatogram allows both qualitative identification by retention time and quantitative measurement by peak area of a substance. Its wide range applications makes it indispensable tool in modern science and industry. So the reference of the following presentation is here. So at last, I want to thank BSIS 2025 for providing an excellent platform to share and develop ideas in front of the brilliant minds, and Dr. Homnath Luitel, HOD of my department, for his expert guidance, mentorship, and for the opportunity to participate in this program. And my dear friends, for their constant support, feedback, encouragement throughout the preparation process. Thank you.
Thank you, Thomas. Now
Thanks, sir.
I ask one question,
Yes, sir.
Thomas. What actually the key features of HPLC?
Sir, the key features of HPLCs is very it works in very high pressure, which results in very rapid and fast processing of the information.
But before you, Tasi told that fast protein liquid chromatography, FPLC,
Yes, sir.
which one is better for detecting
Sir, it
the?
is directly related to what we want. That if we want a very fast way of determining the components of the mixture, we use HPLC. And if we want uh, if we want to do separation of very large molecules, we use FPLC.
FPLC, right?
Yes, sir.
Okay. Any other question from outside? Thank you.
Thank you, sir.
Next presentation, Tapas Rai.
Yes, sir.
Tapas, you are here?
Yes, sir.
Okay. You please
Yes, sir.
start
I'm
your
just.
presentation.
Am I audible? Hello, hello. Hello, hello.
Yes, yes. You can start.
A very warm good afternoon to everyone present. Today, I, Tapas Bhattrai, a master's student from Narbadur Bandari Government College, would like to present a short and crisp presentation on the topic of scanning electron microscopy. And the plan of my talk would be, firstly, I will begin with a brief introduction to scanning electron microscopy, what it is and why it's important. And we'll move on to discuss its main components, explaining the role of each part, and further we'll discuss the principle and working mechanisms of SEM, that is scanning electron microscope. And after that, we will see the advantages and limitations of this technique. And finally, I will cover some applications. And lastly, I will just show how AI is now being used to improve SEM imaging. So let's start. So SEM, it is an advanced analytical imaging technique that uses a focused beam of high energy electrons instead of visible light to scan the surface of a specimen, and which in turn it provides images with extremely high resolution, which is typically around 1 to 10 nanometers, and magnifications up to 300,000 x, which allows us to observe even the finest nanoscale features. And another major advantage of SEM is that it gives 3D imaging, which helps us to visualize how the surface actually looks. And because of all these capabilities, SEM has become an important tool in the field of research, industry, nanotech, and life sciences. So, one of the major components of SEM are here. So, firstly, would be the electron source or the electron gun. This is where electrons are generated, and usually it is of tungsten filament or filled emission gun. And the other part would be the conventional and objective lenses. These are electromagnetic lenses that focus and control the diameter of electron beam to a fine point. Other would be the scanning coils, which they move the focused beam across the sample in a roster pattern, that is line by line, to build the image. And detectors. So different detectors are used to capture various electrons, that would be secondary electrons, backscattered electrons, and X-rays, to give different information about the sample. And the other would be the vacuum chamber. The entire setup operates under high vacuum to prevent electron scattering by air molecules. And finally would be the display or the computer system that converts the detected signals into digital images that we see on the monitor. So now we're going to look into the principle of SEM. So the basic principle of SEM lies in electron sample interaction. So when the primary electron beam hits the specimen, it generates different signals. Okay. So firstly would be the secondary electrons. These are low energy electrons which are emitted from the sample surface, and this gives us the details about its fine surface details. And second would be the backscattered electron. The primary electrons reflected back, showing contrast with the atomic number. That is, heavy elements would appear brighter. And third would be the characteristic X-rays. These arise when inner shell electrons are displaced, allowing elemental analysis when used with energy dispersive X-ray spectroscopy, that is EDS. And with all these, the intensity of these signals is collected by the detectors and mapped into an image. So the working of SEM would be the electron beam is generated by the electron gun, and it passes through the conventional and objective lenses that focus into a tiny nanometer size spot, and the beam then scans across the specimen surface in a roster pattern, that is line by line. And as it interacts with the surface, those different signals which get generated, like secondary electrons, backscattered electrons, and X-ray electrons, are captured or detected. And these detectors collect these signals and convert them into electrical output, which is further processed by the computer system into an image where brightness and contrast depend on the number and type of electron detected. And the result is a detailed 3D image of the sample surface. So
Now we're going to discuss some of the advantages. Some of the advantages that SEM offers. So firstly would be the high resolution and magnification, which enables us in viewing structures at nanometer scale, and would be the larger depth of field, that is 3D view. And other would be it could provide morphological and compositional, that is with when paired up with EDS information, especially when combined with. So and other would be its non-destructive, a wide range of sample sizes and shapes. And compared to transmission electron microscopy, if we compare it, SEM is faster, more versatile, and easier for surface imaging. However, it has some of its limitations, and some of its limitations would be expensive instrument and requires a skilled operator, and SEM must work in environment, which makes it unsuitable for living or wet samples. And third would be non-conductive samples need a thin metal coating such as gold or platinum, which can sometimes alter the natural surface of that uh, particular sample. And other would be it's mainly a surface imaging technique, so internal structures can't be observed. And lastly would be the electron beam. The electron beam may cause damage to the delicate to heat sensitive materials or the samples. So those were the limitations. And here are some of the applications of SEM. It is used in various fields. Firstly, material sciences to study uh, grain boundaries, fractures, surfaces, corrosion, thin films. It is also used in biology and medical medicine, that is to study cell morphology, microorganism tissues, in nanotech, in forensics, electronics, and industries. And side by side, this is an image of an nanoparticle, an aluminum nanoparticle, which has been captured from SEM itself. And these were some of its applications. So now we're going to discuss how AI is AI has been integrating with SEM for smarter and faster image processing. So mainly the deep learning algorithms, that is mostly CNN based. These algorithms are being used uh, to reconstruct and to reconstruct fine features or to understand the details of various samples. As this AI also and as this use of AI improves clarity of nanoscale structures without increasing electron dose, and it also enables automatic detection, pattern recognition, and quantitative feature analysis in materials. And this image here is an image which shows how AI is helping in SEM analysis upgradation, as this is a recent publication where the author was able to develop a model, PTSR, that is Texture Transformer Super Resolution Network, which could enhance the quality and resolution of SEM images. And it works like, firstly, the idea is to overcome the limitation of long scanning times and possible sample damage that can happen when we capture high resolution SEM images. So what we do using this model is, first we capture a low resolution image quickly, and then use AI to reconstruct the missing fine details. On the left, you can see the stack of reference images. These are high resolution SEM images of similar materials, and they act like a database or a texture library for that AI model. And the reference selector compares low resolution input with all the references images and automatically picks the one that has the most similar texture or pattern. And both the selected references and the low resolution input are then fed into the texture transform super resolution network, which is a deep learning CNN combined deep learning, which inside this network, the system intelligently transfers textures information from the reference to the input image, making the details that were not visible on that were not good, generating a super resolution image using all those reference stacks and model. And this is how AI is being used to in AI. AI is being used to enhance the SEM upgrade analysis. So lastly, I would like to conclude by saying that SEM provides high-resolution surface imaging and compositional analysis at nanoscale. It is widely used in research, nanotech, material science, and industries. However, it has its limitations that include high cost, vacuum requirement, and sample preparation needs. However, the advancements like AI-based imaging are enhancing its accuracy and efficiency. So these were some of the references that I have used to collect the data that is required for making of this presentation. And acknowledgement. I would like to express my heartfelt gratitude to my teachers, especially to our HOD sir, Dr. Naunat Little sir, and other mentors who were also involved in this for their constant guidance and support. And I'm also thankful to my classmates and friends, and also to the team of Basis 2025 for providing such an amazing platform for students to learn something and present something. And this was the end of my presentations. So I would like to say thank you.
Thank you, Tapos. Uh, one question,
Yes, sir.
can I ask you?
Yes, sir.
What actually the information we will get from
Yes, sir.
that? What informations we can gather
Yes, sir.
from the uh, secondary electron or backscatter electron or XRD?
So secondary electrons gives us the morphological analysis of that of the morphological analysis or the morphological structure, basically secondary electrons. And the backscattered electrons, they give us, what was that? So it gives us the what type of elements are those elements, heavier elements or those because backscattered elements uh, give us the atomic number. Simply we can say atomic number, because the more heavier the nuclei would be, the it gives the contrast, basically backscattered electron, because the heavier the nuclei, the more the contrasting brightness would be of that specimen.
There is a EDS system, na? Energy dispersive X-ray system,
Yes, sir.
EDS.
That when paired with that, we get the compositional value of that specimen, sir. What it is composed of.
Yes. So that compositional elements detected actually from that atomic number or heavy element or lighter element in that way, right?
Yes, sir.
So backscatter electron, what information can give?
Backscattered. Hello.
Backscatter electron.
So those backscattered electrons are those electrons um, which are elastically scattered back out of the specimen, and these gives us the contrast or various intensity patterns uh, of that sample.
It. Okay, any other question? No. Okay, thank you, Tapas, once again.
Thanks.
Next data, Seri Vitia.
Yes, sir.
Okay, you can start your presentation.
Okay, sir. So, good evening everyone present over here. Respected research professor, teachers and my fellow participant, myself Chiring Engchinla Bhutia, pursuing MSc Physics from Narbadur Bhandari Government College, Gantok, East Sikkim, is here to give a talk on the topic dynamic light scattering and molecular mass. So, this is the plan of talk that I'm going to discuss throughout this session. So we will discuss the introduction, working principle of DLS, correlation function, application and conclusion. So you might be wondering why the term dynamic light or dynamic. So DLS or dynamic light scattering is dynamic because it is not just a static measurement of scattered light, it specifically tracks how the scattering changes dynamically as a function of time due to ongoing particle movement. So moving ahead, here comes the introduction. Let us know what is DLS or what is dynamic light scattering. So, dynamic light scattering is a technique used to determine particle size distribution in solution. It is particularly significant for characterizing nanoparticles and proteins. And this technique is sensitive to dynamic properties, meaning it measures how particles move in solution, reflecting their physical and chemical environment. So, and the core phenomenon behind the DLS is this Brownian motion. So, Brownian motion of particle suspended in a is the random motion of particle suspended in a fluid. The randomness is fundamentally related to particle size, that smaller size move faster while larger one move more slowly. So you can see here in the diagram that it has a zigzag path representing how a small particle is jostled by collision with molecules of the surrounding fluid. This motion is tracked over time to determine speed and by extension particle size. So moving ahead, here comes the Stokes-Einstein equation, which relates particle size to particle motion or gives the relationship between Brownian motion and particle size described by the Stokes-Einstein equation that is given below. D equals to kBt by 6 pi r eta. So where D is diffusion coefficient, Kb is Boltzmann constant, T is absolute temperature, R is molecular radius or hydrodynamic radius, and eta is the viscosity of the medium. So moving ahead, we have a hydrodynamic radius. So now the diffusion coefficient is related to the hydrodynamic radius through the Stokes-Einstein equation. So let us know what is hydrodynamic radius. So the hydrodynamic radius is the effective size of a molecule in solution, defined as the radius of a sphere that disperses at the same rate as the molecule. This radius is affected by factors such as ionic strength, surface structure and shape. So you can, as you can see in the figure, there are three different particle shape: sphere, cluster of sphere and elongated sphere, illustrating the concept that the major sites include not just the core but the surrounding solvent layer as well. So moving ahead, here is the working principle of DLS. So DLS work by assigning a coherent light or ledger on a sample and capturing the scattered light over time. So you can see in the graph plotted here, the smaller particle cause more rapid intensity fluctuation in the detected scattered light due to the faster Brownian motion, where the larger particle so slower intensity fluctuation as compared to the smaller particle. So here comes the experimental setup of DLS. So you can see in the figure at the beginning of the setup, we have a laser source. This laser emit a monochromatic light beam which is directed towards an attenuator. The purpose of the attenuator is to control the intensity of the laser light to prevent excessive power from damaging the sensitive component or causing measurement errors. So then the attenuate laser beam then passes through a cell containing the sample particle suspended in a liquid. Then this microscopic particle undergo constant motion due to the Brownian movement. So when the incident laser light hits this particle, they scatter in various directions. So a detector, usually a photomultiplier tube, is positioned at a specific scattering angle to collect the scattered light. This particle angle is important because it influences the analysis of the particle size based on how the light waves interfere. So now the scattered light captured by the detector is converted into an electrical signal which is proportional to the light intensity, and these signals further then is amplified and filtered through an amplifier discriminator to improve signal quality by reducing the noise. Next, after that, what the process signals are sent to a digital signal processor, which is known as correlator. This correlator analyzes the time independent fluctuation in the intensity of the scattered light. This fluctuation happens because of the random motion of the particles. So now by calculating the correlation of this intensity variation over time, the instrument determines the diffusion rate of the particles. So the diffusion rate is directly related to the size of the particles in the sample. And finally, a computer receives the data from the correlator and uses sophisticated algorithms to quantify the particle size distribution, giving us the valuable insight into the sample characteristics. Sorry. So now here comes the correlation function. So the correlation function is denoted by g tau. So it's a statistical measurement of how the intensity of scattered light at one time is related to that observed at a later time tau. This mathematical function is used to determine how quickly the signal changes, that is, how fast the particles are moving, Then the formula is provided below, where tau is the delay time, and it plus tau are the scattered electric fields at times t and t plus tau. So moving ahead, here comes the application of the DLS. So DLS is dynamic light scattering, is widely used to measure the hydrodynamic size of nanoparticles, proteins, and biomaterials. It also helps to study the stability of nanoparticles as a function of time. It is also good for detecting the aggregation of particles, and it also helps to determine of diffusion coefficient. So now we are at the end of this presentation, or we are at the very end of this presentation. So the conclusion part. So DLS accurately measures particle motion by analyzing fluctuation in scattered light. The rate of motion reveals the hydrodynamic radius, and the Stokes-Einstein equation connect diffusion rate to physical size, and it is reliable for estimating the molecular mass when the shape is known. So now we had came to the, so this is the reference that I had took from, and now we had came to the end of the presentation, and I would like to express my sincere gratitude to the organizing committee of BASIS 2025 for providing me with this wonderful opportunity and platform to present this presentation today. And I would also like to thank our Sir Dr. Homnath Nutel, HOD of Narbadar Bhandari Degree College, Tadu, for his constant support and valuable guidance throughout this work. And I would also like to thank my friends for helping me with lots of good ideas to bring up in this work. Thank you.
Hello.
Hello.
Bhutia.
Yes, sir.
Are you hearing
Hello.
me?
Hello. Yes, sir. Hello, sir.
Yeah. So what actually the basic principle of this signal, optical signal to electrical signal?
Yes, sir. What? I,
How the optical signal can convert to electrical signal in your instrument, in this instrument actually?
sir, how optical signal convert to sir, electrical signal, sir?
Yes.
Mm, So the principle of converting an optical signal to the electrical signal is, sir, it is based on the photovoltaic or the sir photoconductive effect. Sir, where, there is a photo detector which converts our incoming photons into a sir a flow of electrons.
So what type of photo detector is there? Can you know? Would you know?
Photo detector, sir.
Uh-huh. There are a number of photo detectors, silicon photo detectors. There are PMT photo detector and other photo detectors also.
Or photodiode,
So
phototron.
that. Okay. Any other question from the audience? Hmm. Okay. Thank you once again.
Thank you, sir.
Next is Amit Sharma.
Yes,
Amit.
sir.
Yes. You can go ahead.
Yes, sir. Sir, is it visible? Hello?
Hello. Amit, you can start your presentation.
Hello, sir. I'm not being able to share my screen.
Oh.
Sir, I'm not being able to share my screen right now.
Then?
Can I disconnect and try it again?
Yes. Yes. And again join.
Yes, sir. Sir, it is visible right now. Yes. Is it? Hello?
Yes. 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 It is visible.
Is Amit Sharma, and today I will be talking about electrospray, MSI, and MOLD. So, first, let us look at the plan of the talk. So, in this presentation, I will be covering electrospray ionization, that is ESI, and working of ESI and its advantages. Then we will be moving on to mass spectroscopy, that is MS, and we will be the work of mass spectroscopy, and we will be comparing ESI with MOLD. Last, we have the applications. and the concept of torque. So let's start with the electricity. So what is electricity?
You-
So it was invented by Joydev. Joydev is a technique that uses a strong electric field
Your screen is not
to
visible. Amit.
power supply using the So in this electricity, electricity physics and small transformer convert to electrons and molecules. So this explanation technique is used as a soft ionization method, especially in microspectrometry for analyzing large biomolecules like proteins or DNA. So here, soft ionization method, by soft ionization method, we mean that very minimal energy is used for this ionization process. So samples that are fragile, like in this case, the large biomolecules like proteins or DNA, they do not undergo fragmentation. So for this, soft ionization method is used, and electrospray ionization is mostly preferred. And the next point, it generates multiply charged ions without fragmenting the molecules. So multiple charged ions are generated and there is no fragmentation of molecules of the sample. So moving on, let us learn how electrospray ionization works. So we can refer to this diagram that I have here. This is the representation of the electrospray ionization process. So at first, we supply the ESI with a high voltage,
No, your
usually
screen is not
around the range
moved.
of 2 to 5 kilovolts,
Amit.
and it is applied to a capillary sample. So
Hello?
here we can see there is a 2 to 5 kilovolt of power supply present, and the positive end of this power supply is connected to the spray needle. Yes, sir.
Amit, Amit,
Your slide is not moving.
your slide is not moving.
Yes, sir.
Light is not moving.
Yes, sir.
Amit, you can start your presentation again.
Sir, Amit is saying his network connection is very weak.
Okay, then we can go to next page. Okay. Then you can ask to Devyani Rai. Are you here,
Hello?
Devyani?
Yes, sir.
Hello.
Hello, sir.
Okay, you can start your presentation.
Okay, sir.
Yes.
Sir, are the slides visible?
Yes, yes.
Okay. So, good evening, everyone present out here. Respected members of organizing committee, learned professors, and all the presenters of this webinar. So, here I am with the topic affinity chromatography, which is a selective purification technique based on biological interactions. So, the highlights of the sessions are as follows. So, first of all, we need to understand what is chromatography, affinity chromatography. So, affinity itself is a word which is going to describe this type of chromatography. So, affinity means attraction to something. So, in the picture, as you can see, some of empty spaces, structures attached to the wall, and in between, there are many shapes like circle, square, hexagon, etc. So we can understand that hexagon shape will only perfectly fit in that empty shape. So affinity chromatography is a type of liquid chromatography which is selective and specific, relying on the binding affinity between target molecules and a ligand immobilized on the solid support. So it enables the purification of target biomolecules based on their biological structures and functions. Moving on to the next slide, we have got this. So, what is so special about this binding? So, this binding occurs between ligand and target molecules. So, first of all, we have the highly selectivity of this kind of binding. So, the principle is primarily based on the ability of a biologically active molecule to bind specifically to a ligand which is immobilized. The working mechanism is often associated with the lock and key mechanism of enzyme substrate interaction. Secondly, reversible bond. So it utilizes the reversible biological interaction between components in the mobilized mobile phase and a solid stationary phase of separation. Thirdly, optimized condition. So the bound substances are recovered and the affinity between bound substances and the ligand breaks by using a competitive ligand by changing the pH, ionic strength, etc. So now we have the key components of the system. First of all, there is matrix. So the matrix is chemically and physically inert support that couples a ligand. It should have a relatively larger surface area for better ligand attachment. It must be insoluble in solvents and buffer, which is used in the purification process. The matrix, for example, the matrix can be used as agarose, cellulose, or polyacrylamide, or etc. So secondly, we have ligand. So ligand, it refers to the molecule attached to the matrix which reversibly binds to a specific target molecule. The selection of a specific ligand depends on the nature of the target molecules. Some of the examples of ligand can be antigen, which is used as a ligand for antibody isolation. Third is the spacer arm. So is the spacer arm is the one which connects the ligand to the matrix. For example, a 1,6-diaminohexane can also be used as a spacer arm. So in the image, you can also see that the gray surface, which is the matrix, and the stick-like figure, which is joining the bob and the matrix. That stick is your spacer arm, and the small bob is the ligand, and the darker shade of blue, it represents the target molecule. So the next slide shows the steps which can be followed in this affinity chromatography. First of all, we need to prepare the column. The column is filled with matrix. The ligand is selected according to the nature of the target molecules. Second is the loading of the sample. A solution containing a mixture of substances is poured into the column and allowed to flow through it. The sample is applied in conditions that favor the specific binding of the target molecules to the to complement to complementary binding target. So thirdly, we have washing. The washing of the contaminants which are present in the sample. So the contaminants which remain unbounded with ligands are washed away using a washing buffer. Fourth and the last is your elution. Target substances bind specifically but reversibly and are removed by using elution. So this is performed specifically using a competitive ligand or by changing the pH, ionic strength, and polarity. So the target protein is collected in a purified and concentrated form. So this slide represents the diagrammatical representation of the steps which are followed. First one is the preparation of column. Second is the loading of sample. Third is the washing of the column. And the last is your elution. So here we are with the applications which are based on the life sciences. First one is your therapeutic protein purification. So drugs which are made from proteins like insulins, antibodies, interferons must be extremely pure to meet pharmaceutical grade standards. So it actually helps to achieve 95 to 99% of purity. So it preserves the natural structure and biological function of the protein using mild binding or elution conditions. The second is your drug target discovery. So it plays a vital role in the modern drug discovery research. So it helps to find which protein in a cell bind to a drug candidate, revealing potential therapeutic targets. So the technique can confirm whether a drug binds to its intended target or interacts with off-target proteins. Third is your diagnostic and analysis. So here, it enables specific detection, isolation, and quantification of biomolecules such as proteins, hormones, antibodies, etc., and which makes it an essential tool in disease diagnosis. So it also helps to measure concentration of specific proteins, hormones, or drugs in body fluids. Now, this is the pictorial representation of the data which I have taken out from one of the journal I had come across while preparing this presentation. So it represents the data of uses of affinity chromatography in various fields. So moving to the another slides, why this affinity works the best, or moreover, we can see it the advantages of this affinity chromatography. First, we have been talking about this from the very beginning of the slides. That is your high specificity. Second one is the high resolution that it gives. It can actually separate the target molecules with an excellent resolution. Thirdly is your high capacity. So it can purify large quantities as well. Last one is the concentration. So by the process of binding and elution process, it concentrates the target molecules as well. So now moving forward to the limitations and troubleshooting, here we have the ligand leakage. So loss of ligand contaminates the final product. Second is your non-specific binding. So some impurities weakly binds to matrix or spacer arm itself. Thirdly is the high cost. Specialized matrices and ligand can actually be expensive sometimes. The last one is the harsh elution. So because of harsh elution conditions, it can actually denature the target protein. So how can we prevent such errors? So some of the practical tips are given down. So we can include mild detergents or salt for the process. Second, we can explore the competitive binding to maintain target integrity or by doing gentle elution. Last one is your proper storage, regular maintenance or proper storage and sanitization, which can extend the column lifespan. So coming to the conclusion part, we have the following points. So we understood from the slides that affinity chromatography is one of the most powerful and precise techniques for purifying biomolecules. By utilizing specific biomolecules interaction, it provides high selectivity, purity, and yield. Despite its cost and complexity, it remains an essential tool in biochemistry, molecular biology, and pharmaceutical industries for the purification of enzymes and other biomolecules. So these are the references that I have taken out that I have referred for this presentation. So lastly, for the acknowledgement part, I would like to offer my gratitude to the organizing committee for offering such a platform where we can expand our horizon of knowledge. I would also like to express my hearty gratitude to Dr. Honat Lutel, HOD Department of Physics and BBGC Sikkim University for supporting, guiding, and encouraging us to participate in this webinar. Lastly, I'd I'd also like to offer my gratitude towards my friends who are actually supporting and encouraging me. And lastly, thank you to everyone present out here for listening to my presentation. Thank you so much.
Thank you, Devyani Rai. One question is there. Can I ask you?
Yes, sir.
Suppose a metal ion,
Yes, sir.
immobilized metal ion.
Yes, sir.
Can it be purified using this column, affinity chromatography?
So, metal ion. So,
Suppose
metal
metal
ion.
ion like nickel or cobalt or iron, they are attached with the mm,
Yes, yes. So, I think it has a different name for this process. It's ion exchange chromatography, I think so. So
oh,
this affinity chromatography is kind of different.
oh. So only the complex mixture can be purified using this ligand process.
Yes, so
Is it?
like biomolecules and yes, sir, biomolecules and all.
Okay. Okay, fine. Thank you.
Thank you, sir.
Next presentation.
Hello,
Uh,
sir.
Amit is there. Amit? No. Next is Arpana Chetri.
Yes, sir, it's my turn.
announcement সোমনাথ গিরি এই সোমনাথ আচ্ছা সোমনাথ গিরি আছো
Yes, sir, I'm present.
হ্যাঁ তোমার কিন্তু লিঙ্ক ওয়ানে
Okay, sir.
না তুমি তো লিঙ্ক টুতে আছো ফিজিক্সের স্লটে আছো তুমি লিঙ্ক ওয়ানে চলে যাও
Okay, sir. ঠিক আছে।
হ্যাঁ, ওখানে যেভাবে চেক করে তোমার আছে প্রেজেন্টেশন
Okay.
So, Aparna Chetri,
Yes, sir.
please start your presentation.
Yes, sir. Good evening to everyone present. Myself, Arpana Chetri from MSc Physics of Norbadur Bandari Degree College. Today, I am here to present a presentation on the title Application of Dynamic Light Scattering, Protein Aggregation Studies in Biotechnology. In this presentation, I will be going through the following plan of talks: introduction, mechanism, analytical technique, role in neurodegenerative disease, and conclusion. Let's begin with the introduction. Before moving to the main part, let us first know what is meant by DLS. It is a technique used to determine the particle size distribution, and it also helps in characterizing nanoparticles and proteins. Moving to the next slide, protein aggregation studies in biotechnology. This process begins with a newly transcribed mRNA strand which carries the genetic instructions for making a protein. As you can see in the figure, this mRNA is translated into a folded protein. The functional property structure from of the protein. Sometimes, due to errors in folding or changes in the cellular environment, the protein may not achieve its correct structure, resulting in a misfolded protein. So next slide, protein aggregation. Actually, protein aggregation referred to the phenomena where proteins misfold and clump together, either forming soluble or insoluble aggregates. This process can occur naturally within cells or result from certain industrial biotechnology processes. Importantly, while protein aggregates can play a harmful role in the context of disease, especially neurodegenerative disorders. So, moving to the next slide, the mechanism of the protein aggregation. This figure illustrates the process of protein folding and potential outcomes of misfolding. As you can see in the figure, that is nascent polypeptide translated from ribosome. The process begins with a newly synthesized polypeptide chain being translated from ribosome. This is the initial step in a protein synthesis where the genetic information from mRNA is translated in a sequence of amino acids. Then, next process is the formation of partially folded monomeric unit. After translation, the polypeptide chain starts to fold into a partially folded monomeric unit. This is an intermediate state in the folding process. And then the formation of native protein. Under normal condition, the partially folded monomeric units continues to fold into its nature functional conformation. And then the stress causing factors. These factors is that stress causing factors like pH changes, temperatures, fluctuation, etc. can interfere with the proper folding of the protein. This stressors can lead the protein down pathway of misfolding and then the formation of partially misfolded protein to formation of misfolded protein to formation of amorphous aggregates. When stressors affect the folding process, the protein can become partially misfolded, leading to a misfolded protein can then aggregate into either amorphous aggregates. And this mechanism shows the pathway of the protein folding from translation to the native state and highest, how stressors can lead to misfolding and aggregation. And moving to the next slide, it is analytical techniques for studying aggregation. Modern advances in both analytical and computational approaches now allow scientists to better predict, detect, and control protein aggregation events. The use of highly sensitive and specific tools is improving the reliability of the therapeutic protein products and preventing unwanted immune responses in patients and spectroscopy, microscopy, light scattering, and chromatography. And moving to the next slide, role in neurodegenerative diseases. As you can see in the figure is that this application of dynamic scattering in detecting protein aggregation related to neurodegenerative diseases. Now, dynamic light scattering. It is a technique used to measure the size of in solution by analyzing how the light scatters off them. The diagram shows a representation of DLS with a light beam hitting particle in a solution and a graph like representing the scattering data. And then the DLS measure the hydrodynamic radius of particles, which is the size of the particle as it moves through a solution. And this diagram depicts this with a blue shape containing a smaller shape indicating particles in a solution as you can see in this picture. And then the diagram connects the measurement of hydrodynamic radius to protein aggregates. These protein aggregates are associated with the neurodegenerative disease as shown by the illustration of this purple circle representing protein formation aggregates. And this twisted pink structure next to the protein aggregate might symbolize the pathological structure that is seen in a neurodegenerative disease. And moving to the next slide, that is protein aggregation in a biopharmaceuticals. As you can see that this diagram illustrates the process of protein aggregation in biopharmaceuticals. Starting point monomer, the process begins with monomer, which is a single protein molecule. And then the monomer progresses to form a intermediate aggregates, which are clusters of a few protein molecules coming together. And then this intermediate aggregates further combine to form large aggregates, as you can see in that picture, which are bigger cluster of protein molecules. And in biopharmaceuticals, protein aggregation can be a significant issue because it can affect the stability, efficacy, and safety of the drug. An aggregate can lead to change in the drug properties, potentially causing issues like reduced potency, increased immunogenicity, or other effects. And to my conclusion, last with my conclusion part that protein aggregation in a double-edged sword, being a source of disease as well as the critical challenges in a biopharmaceutical engineering, a deep understanding of aggregation mechanism coupled with modern analytical methods aids both in safeguarding biotechnology products. And these are the references from where I prepared the above slide. And next, I would like to express my sincere gratitude to organizing committee of BASIS 2025 for providing me with this wonderful opportunity and a platform to present my work. And also, I would like to express my sincere gratitude to Dr. Homnath Vitesa, head of the department, and also like to thank my friends for their constant support. Lastly, here I have a spectacular view of Timothy Garden, one of the largest tea producer of Sikkim. I hope you guys like it. Thank you.
Okay, thank you. Any question from audience? Okay, thank you again. Next is Deepa Chetri.
Yes, sir.
You can start your presentation.
Good evening, everyone, respected resource person, teacher, and my fellow participant. I, Deepa Chetri, I'm currently pursuing my MSc from NBBGC Tadong, affiliated to Sikkim University. Today,
Then,
I'm presenting on the topic Transmission Electron Microscopy, TEM. These are the plan of talk, introduction, working principle, how does TEM work, applications, advantages and limitations, then the conclusion. Moving on to the introductory part, transmission electron microscopy, TEM, is one of the type of electron microscopy. It is a powerful imaging technique that uses a high energy beam of electrons transmitted to an ultra-thin specimen to produce highly magnified images. Because electrons have a much shorter wavelength than visible light, TEM achieves much higher resolution, allowing visualization of structure at the atomic scale. TEM is widely used in many fields. This technique was first developed by German scientists Max Knoll and Hans Ruska in 1931. Later, Hans Ruska was awarded the Nobel Prize in Physics in 1986 for this work in development in TEM. Moving on, we have principle of TEM. TEM works by transmitting a high energy electron beam through an ultra thin specimen. Electromagnetic plane focuses the electron beam onto the specimen and then magnifies the electron that are transmitted through after interacting with the sample. The transmitted electron carry detailed information about the internal structure, which is projected as a highly magnified image onto a screen. Due to the short wavelength of electron compared to visible light, TEM achieves resolution at the atomic scale, revealing fine structural and compositional details of the specimen. Now let's see the how electron interacts with the specimen. As I said earlier, TEM uses a high energy beam of electron. When a very thin sample is bombarded by this beam of electron, there are several distinct paths the electron can take, and each path carries different information. Transmitted electron form the main image by passing through the sample. Elastically scattered electron deviate without losing energy and provide information about composition and electronic state. Some electron appears as the signal like auger, EDS, or backscattered from the source, and all contributing to a richer set of data beyond just the image. In short, we can say that multiple interaction channel exist. Transmission for imaging, scattering for crystallography, and other signal for chemistry and surface properties. Now let's see the main component of the TEM. In the picture, we can see that the first we have electron gun. It consists of V-shaped tungsten filament which provides stable beam of electrons using thermoionic emissions, which means that when you apply electric current to the tungsten filament, it gets heated up and radiates electron by the process called thermoionic emission. Next one we have is the electromagnetic or condenser lens. This uses electromagnetic lens to focus and control the intensity onto the thin specimen. Moving on, we have specimen stage. This holds the ultra-thin specimen in place. Electron pass through this sample for imaging. Then the objective lens. This focuses the transmitted electron after they pass through the specimen to form a magnified image or diffraction pattern. Last, we have the imaging system. TEM uses a screen at the base of the microscope column, which produces light. When transmitted electron strike it to form 2D image of sample source. Then it maintains inside electron column to prevent electron scattering by air molecules, ensuring beam coherence. This was the main component of the TEM. Now let's see the working of the TEM. How does TEM works? TEM uses a high energy electron beam to create an image. Electron gone at the top of the TEM emits electron. Electron travels through the vacuum in the column of the microscope. TEM uses electromagnetic lens to focus the electron onto the specimen. The electron beam passes through the specimen under investigation. When this electron hits the sample, some electron gets scattered, some gets transmitted. This transmitted electron hits the fluorescent screen at the bottom of the microscope, which produces the image of the specimen. This image is directly studied by computer or photographed using a camera. Now we have the applications of the TEM. First, in material science. TEM provides atomic level imaging of the crystal structure. Researchers can directly visualize gram boundaries, dislocation, lattice planes, etc. That's to detect cracks, voids, impurities, and other defects. This causes failure in metals, semiconductor, etc. This is important in aerospace, automotive, etc. Then in biological science, TEM provides detailed image of the cellular organelle such as nucleus, mitochondria, ribosomes at nanometer resolution. TEM provides protein ribosomes and DNA protein complexes can be visualized using advanced TEM methods, revealing molecular interaction. Then in chemistry and catalyst, TEM allows direct visualization of catalyst nanoparticles on their supports. It reveals particle size distribution, surface morphology, which are important in catalytic activity. TEM is widely applied to analyze thin film in coating, solar cells, and electronic device. It helps to determine layer thickness, crystallinity, etc. Then in advanced physics and resource, scattering in TEM produces diffraction pattern that give information about lattice parameter orientation. This is fundamental in solid state physics and crystallography. Inelastic scattering allows study of the band structure, chemical bonding in advanced material. Used for analyzing defect in integrated circuits, thin film, transistor, and new devices. TEM can pinpoint the cause of the device breakdown, such as contamination, electromigration. This was the application of the TEM. Moving on, advantages of the TEM. The main advantages of TEM includes its exceptionally high resolution, allowing magnification over million times. TEM provides detailed information about the internal structure, morphology, shape, size, which is invaluable in material science, biology, medicine, etc. Additionally, TEM can be combined with other analytical techniques like EDS, EELS for comprehensive elemental and electronic structure information. It provides permanent image. Moving on, we have the limitations of the TEM. In TEM, a thin specimen has to be used. So to prepare this sample, it's challenging and time consuming. TEM is very sensitive to vibration, mechanical instabilities, requiring isolated environment for operation. Then it is very expensive to purchase. TEM generally provides black and white image, lacking color information, unless specialized detectors are used. Moving on, let me conclude the presentation. TEM is a very powerful type of microscopy that uses electrons instead of light to look at very tiny things. Because electrons have smaller wavelength than light, TEM can see much smaller details up to 1,000,000 times smaller than what a regular microscope can see. TEM can show the inside details of tiny objects like cells, virus, material, very high magnification and resolution. However, TEM requires special and careful sample preparation. TEM can damage delicate samples and usually shows black and white image. Despite this challenge, TEM is a valuable tool in science for seeing the smallest details and learning more about world at nanoscale. This presentation, I have taken the references from these sites. I would like to thank the organizing committee for providing this valuable platform to present my work. I am grateful to my college professor, Dr. Omnath Luitel, for his guidance and support. I would also like to thank my friend for their constant support throughout the presentation.
Thank you, Deepa. So TEM and SEM both are the electron microscope, right?
Yes, sir.
So what are the differences between these electron microscopes?
Yes, sir.
What actually the differences?
So actually the main difference is that SEM, that is scanning electron microscopy, images the surface using scattered electron to provide 3D view, while that is TEM images the internal structure by passing electron through a very thin sample to provide only 2D high resolution internal view.
So why you are using that electron for scattering? You can use X-ray for scattering.
So because electrons has very shorter wavelength.
How much?
So around 0.05 nanometer.
So the resolution is high.
Yes, sir. If
What
wavelength
actually?
is, yes, sir.
What actually the resolution?
So I didn't get you.
What actually the resolution of the TM?
So I guess it's up to 0.2 nanometer.
0.2 nanometer.
Yes, sir.
You have heard about the HRTM?
What did you say, sir?
HRTM.
HR?
HRTM.
Oh, HRTM.
High resolution
Yes, sir. Yes, sir.
TM.
Yes, sir. So I heard.
So what the difference between TM and HRTM?
So differences
Uh-huh.
between TEM and
With respect to the application side.
So HRTEM is an advanced imaging mode of the standard transmission electron microscope. The primary differences lies in the label of the details. So HRTEM can resolve the atomic structure of the material, while this TEM can provide high magnification image of the general morphology, composition, and crystal structure.
Particle size.
Yeah.
Okay, thank you, Deepa. Next, Amit is there.
Yes, sir, I am present.
Can we present now?
Yes, sir.
Okay, you can start.
Very good evening, everybody. My name is Amit Sharma, and I will be talking about electrospray, MSI, and MOLDI. Let us look at the plan of talk. We have electrospray ionization, that is ESI. We will discuss the working of ESI and its advantages. Then we'll move on to mass spectroscopy, that is
Slide
MS.
presentation is not here.
Yes, sir.
Slide presentation?
Sir, I am presenting the slide. Sir, it is not being, sir. Sir, is it visible now?
Yes, yes.
Yes, sir. So we will move on to mass spectroscopy, that is MS, and then the working of MS. And after that, we will move on to MOLDI, and then we will compare the ESI versus MOLDI. And at last, we will look at the applications and the conclusion of this talk. So let us start with electrospray. So what is electrospray, or what is electrospray ionization? So it was invented by John Bennett Fenn, and he won the Nobel Prize in 2002 in chemistry. Electrospray is a technique that uses strong electric field to atomize a liquid into a fine particle, into a fine spray of charged droplets, often producing nanoparticles. So here we use electric field. So this electric field is used to reduce the liquid sample from small charged droplets, and these charged droplets, they are further reduced until it produces ions or nanoparticles. So this electrospray, it is widely used as a soft ionization method, especially in mass spectrometry for analyzing large biomolecules like proteins or DNA. So soft ionization method, electrospray follows soft ionization method, and this this method, what it does is the minimal energy is used for the ionization process. So for the samples like proteins, DNAs, which are very fragile, we use this type of ionization method to make sure that the sample does not undergo fragmentation. And the next point is it generates multiply charged ions without fragmenting the molecules. So there are multiple charged ions being generated, and the molecule fragmentation is not there. So moving on, let us talk about how electrospray ionization works. So we can refer to this diagram of electrospray ionization process. So first point is a high voltage of 2 to 5 kilovolt is applied to a capillary sample. As we can see in here, we have a power supply which ranges from 2 to 5 kilovolts. And the positive side of this power supply, it is connected directly to the spray needle. And this spray needle, it carries the liquid sample in it. And the negative side of the power supply, it is connected to the metal plate that is placed opposite to the spray needle. So here in the spray needle, the liquid sample is passed through, and with this liquid sample, we also pass a nebulization gas. So this nebulization gas, what it does is it helps in the formation of fine mist of charged liquid droplets. So now after this, the sample, liquid sample, moves towards the tip of the spray needle. So at the tip of the spray needle, we have a very strong electric field being generated. So the sample ions, which in these cases are positive ions, so the sample ions, they tend to move towards the surface of the, so they tend to move towards the meniscus of the droplet. So now in this case, we can see due to the electric field acting on the liquid, the electrostatic stress, it overcomes the surface tension of the droplet. So due to this, an force is applied from other directions towards the liquid surface, and due to this, it takes the shape of a cone. So this is known as a Taylor cone. So it forms a shape of a cone at the tip of the spray needle due to electric fields. So now what happens is the liquids, it forms a fine mist of charged droplets. So at the very tip of this Taylor cone, when the electric field forces are equal to the surface tension of the droplet, a jet is emerged from the tip of the cone. So this jet that I'm talking about, it is like similar to any type of hand sprays that we have seen in our day-to-day life. So this jet, they form charged droplets. So this charged droplet, it looks like the droplet that is present in here. So the positive ions, in this case, the sample ions, are towards the surface of the droplet. So, and now because this droplet size, it is very tiny, they undergo evaporation. And due to the evaporation, the droplets reduce in size and they undergo ion formation. So what basically happens is the evaporation process acting on these droplets, it reduces the volume of the droplet. So it reduces until it reaches a point where the Coulomb repulsion forces between the ions present inside the droplets, they exceed the surface tension of the droplet. And uh, when this happens, the ions are then there is a fission being created in the droplet, which results in the ion formation. And the required ions that we want, it is passed through the metal plate towards the mass spectrometer. Here, the ions we are studying is plus ions. So the metal plate, which has a negative potential, it helps in acceleration of these plus ions towards the mass spectrometer. And all the other solvents and the neutralized ions, they are captured by the metal plate itself. So the solvent, it evaporates and it leaves multiply charged ions, and these ions enter mass spectrometer for further analysis. And in electrospray ionization, in here, the ions are directly generated from the solution, as we can see from this figure. We use a liquid sample to generate ions. So Moving on to the mechanisms, we have Taylor cone formation that we have already discussed, where the high electric field that accumulates over the surface of the droplet, it it and makes the droplet in a cone shape, and it deforms the droplet into a cone. And the next we have droplet generation, where the jets they break into small charged droplets, and these droplets are contain excess charge of one polarity depending on the applied voltage. So in this case, we have a positive polarity. And next we have evaporation and Coulomb fission. And in this, the solvent are evaporated out of the droplets, and the Coulomb repulsion inside the ions, when they are equal to the surface tension, the droplets undergo fission, and they are further divided into small ions and into smaller progeny. So the process of ion formation, it mainly has two models. So one is charged residue model and the other one is ion evaporation model. So for charged residue model, the solvent molecules, they evaporate and ion is left as a residue, as we can see in this figure given. And for the ion evaporation model, the ions, they evaporate away from the droplet itself. So these are the mechanisms of electrospray ionization. Moving on, we have the advantages of electrospray ionization. So electrospray ionization, it produces multiple charges. So even large molecules, they can be appear within measurable mass range. They cause less fragmentation, which is very helpful in preserving the molecular integrity and making sure that the sample is not deformed in this process. And this electrospray ionization, it is used in proteomics, metabolomics, and pharmaceuticals. So now we have mass spectroscopy. So mass spectroscopy, what is mass spectroscopy? So it is a technique for determining molecular mass and structure. So it measures the mass to charge ratio, that is m by z of ions, and it works like a very sensitive molar weighing scale. So mass spectroscopy, it is used to analyze and calculate the compounds that are present in the sample. And here the mass to charge ratio means that the mass of the particle is divided by the electric charge, that is m by z. And this is used in mass spectroscopy to separate and identify ions based on how these ions are affected in their motion due to electric field and magnetic field. So basically, it means that a higher mass to charge ratio means the particle is heavy but lower in charge, and a lower mass to charge ratio means the particle is lighter but heavier in charge. And mass spectroscopy, it allows us to identify unknown compounds and verify molecular formulas, and it is used in detecting pollutants, studying materials, and biomedical research. So let us talk about how mass spectroscopy works. So the sample is ionized and converted into charged particles. So as we can see in this diagram right here, uh, first we take a sample. So the sample, it can be solid, liquid, or gas. So if the sample is solid or liquid, so it is first passed through a vaporization chamber where it is heated and converted into gas. So the solid and liquid samples, they are converted into gas. And now these gases, they are made to be passed through the positively charged repeller plate that we can see in this figure. And they cross this repeller plate towards the filament. And this filament, this tungsten filament, it produces electrons. It produces electron beams, and the potential is around 70 electron volt. And what this electron does to the sample is these electrons, they attack or they bombard the sample molecules. So when this electron hits the desired sample ion, let's say the desired sample ion is M. So an extra electron is formed when this electron hits the sample. So this results in M converting to a M plus ion with a free radical. After this, the ions that are produced, they are accelerated in an electric field. So after this, the M and the M plus ions, which are known as, they are formed because of ionization potential, and we know that the approx value of ionization potential is like 8 to 15 electron volt, but here in this filament, we have a 70 electron volt potential by the filament. What it does is the M plus ion with free radical, it is again fragmented into two different ions, that is M1 plus ions and M2 plus ions. So there are three total ions that we observe in the mass spectrometer, that is M plus ion, M1 plus ion, and M2 plus ion, where M1 plus ion and M2 plus ion are fragment ions. So all the uh, residue ions molecules like neutral molecules, neutral fragments, and negative ions, they are ejected out of the mass spectrometer using a vacuum pump. So this is done to make sure that the experiment is conducted only on the desired ions. So after the filament, the sample is then moved on into negatively charged accelerating and focused plates. So in between these plates, we have three electrodes present. So the first electrode is positively charged, and the second electrode, the middle electrode, is negatively charged, and the third electrode, which is on the right hand side, is more negatively charged than the second electrode. So the electrode potential is usually between 8 to 10 kilovolt. So the ions are accelerated towards the right side of the instrument. So these ions, they gain acceleration due to this negatively charged accelerating and focus plates. And then the other molecules that are residue molecules, they are vacuumed out of the pump. So these accelerated ions that are M plus ions, M1 plus ions, and M2 plus ions, they experience a deflection due to the magnetic field produced by the magnets that are placed in the instrument. So we can see there are two magnets which helps in producing the certain magnetic field for this experiment. So these ions are then passed through this magnetic field, and what this magnetic field does is it separates the ions according to their mass to charge ratio. So the formula of mass to charge ratio, as we can see, is m by z equals h square r square by 2v, where h is the magnetic field intensity. So, let us, so if we consider the mass of M ion to be more greater than M1 and of M1 to be greater than M2, then due to the deflection caused by mass charge ratio, the M ion, which contains high mass, it uh, it reaches the exit slit first, and then the M1 ion, and then the M2 ion. So this is how the ion exit slits uh, captures these ions. So all the positive ions are detected, and the neutral species are undetected. Uh, so after the ion exit slit, they are transferred into the collector, where these details are collected and is further sent to the recorder, where analysis of these ions are further done. So this is the full working of a mass spectrometer. Uh, so here are the mechanisms of mass spectrometer. We have an ion source which produces ions from the sample. We have a mass analyzer that sorts ions based on mass to charge ratio. And we have a detector that records intensity of these ion signals. And a computer system is attached at the end of the mass spectrometry, which converts data into a readable mass spectrum. And this whole mass spectrometer, it is a vacuum system. So why is it a vacuum system? Is because it helps in maintaining low pressure to allow ions to move more freely. So moving on. So let us now talk about MOLDI. So the full form of MOLDI is matrix assisted laser desorption ionization, and it was developed by Michael Carras and Franz Hillenkamp in 1988. So it works on solid sample mixed with a light absorbing matrix and uses a laser pulse to ionize large molecules gently. So So this MALDI, it is a soft ionization technique. So it helps us in analyzing large or fragile molecules. And here we use a matrix compound. So this matrix compound, what it does is it absorbs the laser energy, it helps in ionization of the sample, and it does this all without any fragmentation of the sample. So it is a soft ionization technique. Uh, MALDI is ideal for biomolecules, polymers, and peptides because they are large and fragile molecules, as I've already said earlier. Uh, and the MALDI, it produces mainly single charged ions. So now let us look at the working principle of MALDI. Uh, these are the working principles of MALDI, and these are the images of a basic MALDI. So So let us look at the working principle. So first, UV laser pulse excites the matrix molecules and energy transfer from matrix to analyte ionization. So first, what happens is the first process is of sample preparation. So we mix our samples with a matrix solution. This matrix solution, it can be a small organic compound that absorbs the wavelength of the applied laser. So the common metrics that are usually used are nicotinic, urea, synapinic acid, and other substances. Uh, now, this mixture of sample and matrix, this mixture, it is placed in a metal target plate, as we can see here, and it is crystallized. So because of this crystallization, the sample molecules and the matrix, they combine with each other, and they form a mixture. And the ratio of this mixture is for one part of sample, we have 10,000 parts of matrix. So the ratio of sample to matrix is said to be 1 is to 10,000. So this is how sample is being prepared. So the second process is laser desorption and ionization. So ions, so the energy are transferred from matrix to analyte ionization, and ions are accelerated into a time of flight analyzer. So what happens is after the sample is prepared, a pulse laser beam, we uh, we attack the sample with a pulse laser beam, which is usually a nitrogen laser beam because it falls under the range of 337 nanometers to 355 nanometers, and it is of UV range. So this type of pulsed laser beams are used, and the laser, it hits the sample with the pulse range of 0 to 5, 0.5 to 20 nanoseconds of exposure time. So this laser, they are pulsated towards the sample. So after this, the matrix molecule that is present in the sample matrix solution, they absorb the laser energy and they rapidly heat up, causing both matrix and the sample to heat up. And this results in ejecting of matrix and sample molecule in gas phase. And these gas phases are released due to the laser action. So in this process, proton transfer occurs between matrix and sample, and thus the sample molecules are ionized without using fragmentation. As we can see on the right diagram here, they are accelerated towards the flight tube using electrostatic field. And now the third and last process of MALDI, which is mass analysis. And at this stage, we have mass analysis where ionized molecules are accelerated to electrostatic field and analyzed by mass analysis, which is most commonly a time of flight detector for MALDI. And what it does is it measures the mass by charge ratio of ions. And using this, it gives us a precise info about molecular weight of the sample. So when the matrix and sample, it is converted into ions, it is converted due to the translation energy, and it further leads into two possible processes. So one process is protonation, where the H plus ion is transferred from matrix to the sample, and the other process is deprotonization, where H plus ion is removed from the sample And in MOLDI, it only produces singly charged ion. So this is the working of the MOLDI. And here we have a comparison table which compares the features of ESI and MOLDI. So for sample type, we use liquid samples in ESI, and solid samples can also be used in MOLDI. And ionization source, we use mainly electric field in ESI, and UV laser plus matrix is used in MOLDI. And the charge states in ESI are multiple. There are multiple charged ions formed in ESI, whereas for MOLDI, there is only single charge ion formed. And the common analyzer used for analyzing the data in ESI is quadrupole or time of flight, and for MOLDI, it is only time of flight. The ESIs is best used for peptides, proteins, and metabolites, and whereas the MOLDI is best used for proteins, polymers, and biomolecules. These both mm, they help in studying the proteins and polymers. And then we have sample preparation, where in which the ESI, we have a liquid sample that is continuously flowing through the needle. And in MOLDI, we have a matrix mixing and drying the sample, and matrix is mixed together at certain ratios and is dried out to prepare the sample. So this is the comparison between ESI and MOLDI. So now let us look into applications of ESI and MOLDI. So for protein analysis, ESI is mainly focused on analysis of proteins in solution with multiple charge states for very large molecules, and MOLDI, rapid protein identification and fingerprinting from solid samples. And for clinical diagnosis, ESI is used to detect disease biomarkers in blood, urine, and other body fluids, whereas for MOLDI, it identifies bacteria and fungi directly from colonies in minutes. And we have pharmaceutical analysis, where ESI helps in monitoring drug levels in blood and body fluids for dosing, and in MOLDI, it is used for screening drug candidates, and it validates pharmaceutical compounds quickly. And lastly, we have polymer and materials. So ESI, it helps in monitoring the polymerization reaction in real time, whereas MOLDI, it determines the polymer composition and molecular weight distribution. So these are the applications. So now we have reached the conclusion of the topic. So ESI and MOLDI, they have transformed mass spectroscopy from a small molecule tool to a universal analytical powerhouse. These both techniques, they provide soft ionization methods, allowing intact molecular analysis, and they make sure that the molecules are not fragmented during the process. And the mass spectrometry, it brings experimental and theoretical domains of modern physics and chemistry together, and they enable unprecedented accuracy in molecular characterization and quantification. So these are the references that I have used in collecting the data for this presentation. And lastly, I would like to express my thanks to the BASIS 2025 for providing a wonderful platform to present our ideas. And I would also like to express my gratitude to Dr. Omnath Duitel sir, our HOD of Physics Department in Narbadur Bandari Government College, Tadung. And we are very thankful for his constant guidance and encouragement towards us. I would also like to thank my friends for their help in making of this presentation successful. And thank you everyone for listening to this presentation.
Thank you, Amit.
Thank you, sir.
So through this ESI and that matrix assisted laser deposition, can we prepare thin film?
Yes, sir.
Can we prepare thin film through this method?
Sir, thin film.
Thin film.
Sir, I didn't understand the question.
Actually, you are using this ionization technique
Yes, sir.
for the large molecules or the number of particles in a substance,
Yes, sir.
right?
Yes, sir.
So
Sir, I think that mass spectroscopy, it does not, sir, I don't think it can prepare thin films.
the deposition technique, that matrix assisted laser deposition technique.
Yes, sir.
So there are different types of deposition technique. Physical and chemical vapor deposition technique, physical vapor deposition technique, like this. So pulse laser deposition technique for preparation of thin film, for preparation of nanoparticles, like this. Can it be used for this? I don't know. Actually, I want to know whether it is possible or not.
Sir, in terms of, sir, for ESI, I think it can be used to prepare thin films. Sir, but for moldy, I am not so sure about it. Sir, I will look into it.
Okay. Okay. Any other questions from audience? No. Thank you once again,
Thank you, sir.
Amit, and all the participants for their valuable presentations. Thank you. Thank you all. Next, Kriti,
Yeah.
are you here? Okay, you can conclude.
Thank you for all students, and a nice presented by all students. And thank you the Dr. Makhanlal Nanda Goswami, the session, chair the session, and the vote of thanks delivered by Professor Sujit Kumar Das. I request you to say the vote of thanks for the today's program.
Sir, I am just waiting to.
One thing, and all delegates, all presenters, on your camera for taking a photo, for a photo session.
Sir, Dejanaba will be joined. Please wait for a second.
স্যার একটা ফোন করে দাও, ফোন করেছ?
হ্যাঁ হ্যাঁ কল করেছি।
Switch on your camera. Yeah. Navakumar, on your camera. Amit Sharma.
Yes, Dejan sir joined. Has joined.
Sajal Bej. Sajal Bej and Amit Sharma. Shubhankar perhaps in now train. So Devyani sir, on your camera. Ready? Sujit, continue the program.
Okay, sir. Am I audible?
Yes.
Yes, sir.
Thank you. Good evening, everyone. It is my privilege and pleasure to propose the vote. Thanks. Hello.
হ্যাঁ শোনা যাচ্ছে বলো।
Yes, sir.
It is my privilege and pleasure to propose the vote of thanks on this wonderful occasion of second day of our 3 days program of Basis 2025 webinar series 1 on presentation and discussion on pure and applied sciences. First and foremost, I extend my heartfelt gratitude to our chief patron, Professor Dr. Sandip Chakrabarti, Director, Indian Center for Space Physics, Kolkata, for gracing this event with your presence, sir, and for sharing your valuable insights on do we focus on space exploration or changing climate mitigation. I believe that students will be enriched by this talk. Our galaxy is unlimited and it also expanding. Discussing anything on this matter is always interesting. I think your valuable discussion will be very much helpful to our students, researchers, science devotees, and all audience. Your inspiring words have truly motivated us to explore the beauty and depth of both mathematics and physics in new way. Once again, thank you to Dr. Chakrabarti sir. I would also like to express my sincere thanks to Dr. Vijendranath Sai, Retired Professor, Ramnagar College, and Guest Professor in the Department of Mathematics, PK College, Kontai. Whatever I say about him, that is not enough to explain about him. When he talks about math, it feels like we are listening to a story. It is so beautiful to hear it from him. Math is a beautiful subject, and it's even more beautiful when you hear it from him up close. I think today those gave the presentation will be encouraged and enriched by the suggestions given by him. I am also thankful for his constant encouragement and support to us to organize this webinar successfully. Thank you, sir. Your guidance has always been a source of inspiration for all of us. I also would like to thank Dr. Abhijit Bera, sir, Department of Physics, Midnapore College, for providing valuable time and constant support to conduct this webinar smoothly. A special word of appreciation goes to Dr. Makhanlal Goswami, President of Basis, Department of Physics, Midnapore College, who mentored and guided us, and whatever we proposed, he always takes it positively. I would like to express heartfelt thanks for encouraging presenters with valuable suggestions. I also would like to express my sincere gratitude to Dr. Kiti Ranjan Sahu, sir, Secretary of Basis and Professor of Department of Physics, HOD, Brathan College, and convener of this event. His immense dedication and hard work made this webinar possible. To our students and presenter, thank you for your hard work and enthusiasm. Your innovative idea and dedication have truly made this program a meaningful academic experience. I would also like to thank all members of BASIS organizing committee for their behind the scene efforts, managing the schedule, equipment and arrangements so smoothly. Last but not least, a big thank you to all our participants and audience members for your attentive presence and encouragement. Your interest and curiosity have made this event lively, and thank you once. Over to you, sir. Dr. Kirti sir.
Thank you. And an announcement. 12th October is the last day of our program, third day, and all are requested to present the 12th October. And 12th October, the special speaker is Dr. Narayan Kumar Shankar Kumar Nath. And in the end of the program, in the valedictory session, once again arrange a photo session. All are, except all will be present in this session and overall this session. So thank you. Next, we will meet again 10 o'clock morning.
Okay, thank you.
Thank you.